Welcome to this explainer. Today, we're popping the hood on the exact architectural blueprint that powers one of the most successful autonomous AI systems in the entire world. We're looking at Claude Code, a system that fundamentally changes how we think about building AI agents. We are going to tear down this engine piece by piece to see exactly how it ticks.
$1 billion. Claude Code hit $1 billion in annualized revenue in just 6 months. And here's the crazy part. They didn't get there just by plugging in some smarter underlying model. They got there through a vastly superior engineering paradigm. Anthropic built the right harness around the right model. It's a total masterclass in software architecture, and today we're going to reconstruct exactly how they pulled it off.
We're witnessing a massive shift in how we build AI. We're moving away from just prompt engineering and getting into harness engineering. Look, think of the AI model like a massive car engine. It provides all that raw reasoning power and decides where to go. But the harness is your chassis, your steering wheel, and your brakes. It actually executes the model's decisions, constrains its actions, and hooks it up to the real world. You can have the most powerful engine on Earth, but without a good harness, you're not going anywhere safely.
So here is our roadmap for today. We'll hit harness engineering principles, the master loop, context and memory, multi-agent systems, production hardening, and finally, future upgrades.
Let's start with part 1, harness engineering principles.
Okay, so what does this actually mean? Well, in harness engineering, the model is the sole decision maker. The harness never tries to branch on the model's output. It just faithfully executes whatever the AI requests. But, and this is a big but, tools are the AI's absolute only interface with the world. Every single action, from reading a file to spawning a subagent, has to go through a typed, schema-validated tool call. Context is strictly managed and permissions are defined declaratively. It's all about creating ironclad structured boundaries. Why? Because an unbounded model is totally unpredictable. But a model wrapped in a strict harness is a system you can actually rely on.
Moving on to part 2,
The master loop.
this single-threaded master loop is the absolute foundation of the architecture. It's a generic perception, action, and observation cycle. And you know what's wild? This piece of code literally never changes. It runs exactly the same whether you're asking the AI to fix a tiny one-line bug or refactor an entire monolithic codebase. The harness receives a task, the model attempts a solution using a tool, the harness observes the result and feeds it back, and then the model decides what to do next. The intelligence lives inside the model, not the loop.
And that brings us to the tool dispatch registry. This is what connects intent to execution. Claude Code ships with about 18 of these registered tools. What's so elegant here is that if you want to add a new tool, you don't have to touch that core loop we just talked about. You just map a tool name to a handler function, and that's it. And the descriptions are hyper-precise. For example, when using the read tool, it specifically returns numbered lines. Why? So the model can explicitly say, hey, replace lines 45 through 67 later on without guessing. The description isn't just documentation. It's a strict functional instruction.
All right, part 3, context and memory.
Have you ever seen an AI just forget what it was doing halfway through a long task? It's the worst. To prevent that drift, Claude Code uses a really clever trick. Before doing anything, the model uses a to-do-right tool to map out a persistent task graph. Then the harness continuously re-injects this game plan right back into the system prompt, keeping the model accountable to its own goals. It also uses something called progressive disclosure for its skills. Instead of just dumping every single rule into the prompt at once, it only loads specific skills exactly when they're needed. It saves thousands of tokens and keeps the AI laser-focused.
Now, to keep the context window from completely overflowing, there's a built-in compressor mechanism. Right when the context hits 92% capacity, this triggers automatically. But it doesn't just delete your history. It takes the older messages and collapses them into a single summary block, while keeping the most recent turns exactly as they were. This summary gets written to a persistent markdown file on your disk. That means the agent's memory is totally durable. Its core understanding survives even if you completely close out your terminal and restart the session.
Let's dive into part 4, multi-agent systems. When you've got a whole team of agents talking to each other asynchronously, you run into the nightmare of deadlocks. You know, 2 agents just sitting there waiting on each other forever. This architecture solves that with a really strict communication protocol. The golden rule? No agent transitions to a requesting state while they're already in a waiting state. By explicitly enforcing these states using a finite state machine, it completely eliminates those deadlocks. The model just calls a delegate tool,
And the architecture safely handles all that messy asynchronous team communication behind the scenes.
But wait, what happens if two autonomous agents try to modify the exact same file at the exact same time? Usually, you'd get a horribly corrupted file. To fix this, Claude Code uses Git work tree isolation. This is brilliant. Every single agent gets its own directory, its own branch, and its own working tree. They are literally operating in completely separate sandboxes. When they're done, the harness compares the branches and flags any overlapping code for human review. It is pretty much the ultimate isolation model.
Moving on to Part 5, Production Hardening.
This is where we go from a cool, fragile prototype to a rock-solid billion-dollar enterprise system. Production hardening brings in real-time token streaming so you can actually see the AI thinking right in front of you. It takes silent file snapshots before every single edit, meaning you can instantly revert if a test suddenly fails. It upgrades inter-agent communication using Redis pub subchannels, which is basically an instant messaging system for AI. It uses event hooks to build out a perfect audit log. And maybe best of all, it uses prompt prefix caching that recycles up to 92% of the system prompt on every API call. That slashes token costs dramatically.
And we absolutely have to talk about permission governance. Using super simple YAML configuration files, you set up strict permission tiers. You've got safe operations running silently in the background, but high-impact stuff, that pauses everything and waits for humans to say okay. It proves that AI safety shouldn't just be a suggestion where you hope the model behaves. It needs to be a declarative, structural wall built right into the environment. The harness simply refuses to run an unapproved tool call, period.
Finally, Part 6, Future Upgrades.
So, we've got a system that's clean, non-repetitive, and rigorously tested. But engineering is never truly finished. To keep pushing the boundaries of autonomous systems, we have to look at what's next for developers building their own harnesses.
You can supercharge this whole setup by spawning sub-agents in parallel, which drastically cuts down on how long the system takes to explore solutions. You can level up from simple text files to a vector database like ChromaDB, giving your AI instant semantic memory retrieval across millions of lines of code. And crucially, you can introduce LLM as a judge evaluation layers. That means using a second AI purely to grade your main agent's reasoning, accuracy, and plan adherence. It turns a functional system into a highly measurable, constantly improving one.
The paradigm has fundamentally shifted, guys. Better prompts just aren't enough anymore. The future entirely belongs to the environment that surrounds the AI, the tools, the memory, the constraints. So the only question left to answer is, how will you architect your own system? Think about how you can take these exact principles and build them into your own projects. Thanks so much for joining me on this explainer, and keep building.